Okay, so before moving to Euclid, let me start with a very short cosmic history. So we have that the cosmic neutrino background was produced only 1 second after the Big Bang, when the temperature of the universe was about 1 MeV. And these neutrinos, neutrinos of the cosmic neutrino background, they travel towards us, they get redshifted, eventually reach us. And you see in this plot that they are the most abundant component of the neutrino fluxes that we receive. However, they are located at very low energy. That's why we don't have a direct detection of the cosmic neutrino background yet. And we have to look for the footprints of the cosmic neutrino background in other cosmological observables. First of all, in the cosmic microwave background, which was produced about 300,000 years after the Big Bang, when the temperature of the universe was much cooler, about 0.2, 0.3 electron volt. And contrary to the cosmic neutrino background, we have indeed directly detected the photons of the cosmic microwave background. And these photons show an almost perfect black body at a temperature about 2.7 Kelvin, with some small temperature fluctuations of the order of 10 to the minus 5. And if you project these temperature fluctuations in spherical harmonics, and then you do a Fourier transform, you can get this power spectrum of CMB temperature fluctuations. So these, the red points are the data from Planck, and the blue line is the lambda quarter matter model, so the cosmological standard model, and you see that it almost perfectly fit the Planck data points. Then these small fluctuations are the seeds for the structure formation in the late universe, in the local universe. So we can look at the large-scale structures of the universe, for instance, with a spectroscopic galaxy survey. We can get a map like this one. This is a map from the DESI survey. And from a map like this one, you can extract several information. For instance, you can extract the baryonic acoustic oscillations, which are basically a preferred scale for the clustering, for the formation of structures. You can also extract the so-called redshift space distortion. So basically, this is the map, and it's almost homogeneous in real space. But if you look at redshift space, you see that there are these filaments, these elongated structures, and these are due to the proper motion of galaxies. Then you can also look at the large-scale structure of the universe with a photometric survey. So with doing imaging, looking at the shapes of the galaxies rather than at the spectra and the position. And looking at the shape of the galaxies, what you can do is to look for the weak gravitational lensing, so basically the statistical distortion of the shape of the galaxies due to the intervening matter field between the background galaxies and us. And with all these different information, what you can do is to do a two-point correlation function, and then you do a Fourier transform, and you extract the matter power spectrum of density fluctuations. So we have information at different epochs, the CMB in the early universe and the large-scale structures in the late universe. But this corresponds also to information at different scales. So the CMB provides information on large scales where we have the linear perturbation, we can use linear perturbation for our theoretical predictions, while the large-scale structures go from the mildly nonlinear regime to the deep nonlinear regime, where we cannot use the linear perturbation theory anymore. We have to use n-body simulation to get our theoretical prediction. But the difference is that for getting a linear prediction, you can use several Einstein-Boltzmann codes, such as class or camb, and the CPU time is less than 1 second, fraction of a second. While for n-body simulations, we need thousands of CPU hours for only one theoretical prediction, so basically 1 point of your model. Now, having this information, different probes at different scales and different epochs is crucial for studying the cosmic neutrino background. Because the cosmic neutrino background has a dual nature. So it behaves as a radiation component in the early universe. So basically, this is the radiation density of the universe, and you can parameterize the contribution of neutrinos and other beyond the standard model light particles through this parameter NF. And for 3 neutrino families, so in the standard model, if you don't have any beyond the standard model light relics, so there are no light sterile neutrinos and so on, no actions and so on, this NF is equal to 3.044. I'm not going through the details of this calculation because this will be the topic of other talks. Let me just say that with the current CMB and large-scale structures, BAO measurements, this NF is very well consistent with the standard model value, so with 3.044. But then, at later times, we know that neutrinos are massive, at least 2 neutrinos are massive, so their contribution to NF drops because they go non-relativistic. And after CMB formation, they start behaving as a matter component, contributing to the hot dark matter density of the universe. It's a hot dark matter density, and it cannot be the cold dark matter of the universe, because when neutrinos decouple, they were still highly relativistic. So they cannot be the main cold dark matter of the lambda cold dark matter model. And what we can measure with cosmological data is indeed the energy density in hot dark matter. And if you assume that there is no new physics, no new interactions, so the cosmic neutrinos of the cosmic neutrino background have a Fermi-Dirac statistics and everything is well behaved, let's say, then from the density of hot dark matter, we can derive constraint on the sum of neutrino masses. So bear in mind that in the remainder of the talk, some people might say neutrino mass, but what I mean is always the sum of the neutrino masses, because cosmology is not sensitive to the individual neutrino masses, okay? So how we can detect the neutrino mass in the cosmic neutrino background? Well, first of all, we can use the CMB. What we have here is the ratio of the CMB temperature fluctuations in a massive neutrino cosmology compared to a massless neutrino cosmology, the reference. So basically, this is the impact of increasing the neutrino mass from massless neutrinos to 0.06 and 0.3 electron volt. And we get the solid lines. So I'm not going through the details of how we get these wiggles here. This is a combination of background effects and perturbation effects. But let me just say that if you do the same exercise, so we increase the neutrino mass, and at the same time we decrease the Hubble constant, then what we get are the dashed lines, which are back inside this gray area. So this gray area is the cosmic variance, and it is an irreducible statistical error. So you can think about whatever futuristic CMB survey, CMB experiment, but you can never go beyond this cosmic variance limit. So what is the message here? The message is that if you take into account only the CMB, you can always vary other parameters of your cosmological model and compensate for the effect of the neutrino mass. So basically, you can hide the effect of massive neutrinos, getting pretty much within cosmic variance the same CMB observable. So this is basically, in a few words, this is a degeneracy. In this case, the degeneracy is between the neutrino mass and the Hubble constant. Okay? So because of this degeneracy that is embedded in the CMB, we have a very tight constraint from the CMB, but we will never have a detection of a non-zero neutrino mass from the CMB alone. What we have here, this is the bound from Planck, from CMB only, temperature and polarization, and CMB lensing as well. And in orange, we have the forecast, the 1 sigma sensitivity of future CMB experiments. This is Simon's observatory, and this is CMB stage 4. The forecast assuming a fiducial value of about 60 millielectron volt. And we see that these are very tight constraints, but still we don't have a detection. In order to get a detection of a non-zero neutrino mass, we need large-scale structure. And why so? Well, because as we have seen before, if the neutrino mass is below about 0.6 electron volt, then neutrinos go non-relativistic after CMB formation. And when they go non-relativistic, they start free streaming. So basically, they travel with a thermal velocity that is larger than the escape velocity from the gravitational potential wells. So neutrinos do not cluster. What we have here are two snapshots of an n-body simulation with standard cold dark matter. Well, this is an n-body simulation with representing the cold dark matter with a 0.5 electron volt neutrino. And what you see is that in the snapshot of with massive neutrinos, many of the small-scale structures are erased. And if we want to translate these images into something more quantitative, then we can look at the matter power spectrum. So this is the ratio of the matter power spectrum in a massive neutrino cosmology compared to the matter power spectrum in a massless neutrino cosmology, the reference. And we see that the more neutrinos are massive, the more they suppress the matter power spectrum. And the effect is actually twofold. So on the one hand, neutrinos do not cluster themselves, and this accounts for basically only 20% of the total suppression. But the remaining, the majority of this suppression is due to the fact that neutrinos slow down the clustering of cold dark matter perturbations. And we see that on top of this suppression, we also have these wiggles here. And these wiggles are due to a shift in the position of the peak that is pointing to the baryonic acoustic oscillations. So basically, you are changing the size of the sound horizon at recombination. And this is leading to these wiggles here. So if you take your BAO data, this is a forecast, it's an old forecast for DAISY-like experiment, and you run your Monte Carlo Markov chain, and then you look at your posterior, and you slice your posterior in the plane Hubble constants versus the neutrino mass. You see that you get a degeneracy that is different from the degeneracy that was embedded in the CMB. So by breaking this degeneracy, you improve your constraint on the neutrino mass. And indeed, this is what it's already happening. So this is the bound, this was the bound from Planck plus old BAO data, and it's improving with respect to the Planck-only bound. And this is the fantastic bound that it was released by the DESI collaboration at the beginning of April, so a few months ago. This is about 72 millielectron volt, 95% confidence level. But since, okay, this is a fantastic bound, but let me just spend a few minutes about this combination CMB plus DESI. So you see this is the posterior of the neutrino mass sum. So this is the green line is the combination CMB plus DESI BAO. And you see that they have this 95% confidence level upper bound of about 72 millielectron volt, which seems to rule out the inverted hierarchy. So this is a great measurement. However, there are some caveats. First of all, this is obtained with a prior on the neutrino mass larger than 0. If instead you replace this prior with a prior motivated by the oscillations, then your bound is about 0.1 electron volt. So inverted ordering is not ruled out anymore. Then the other important point is that this combination of CMB plus DESI does not prefer lambda CDM. So this was one of the great news or challenging news from the DESI collaboration. So this bound, the 72 millielectron volt, is obtained assuming lambda cold dark matter. But actually, DESI prefers a value of W0 and WA that is far away, more than 2 sigma far away from the lambda cold dark matter point. Okay, and if you analyze the data within this W0 WA cold dark matter model, so basically replacing your cosmological constant with a time varying dark energy, then the bound on the neutrino mass sum is about 0.2 electron volt. So basically, if you compute the neutrino mass here in the region that is actually preferred by the data, then the mass is about 0.2 electron volt. Anyhow, even with this DESI BAO measurements, we still don't have an evidence or a detection for a non-zero neutrino mass. And this is where Euclid comes into play. So Euclid is a mission of the European Space Agency. The launch was exactly 1 year ago. The duration is more than 6 years. Euclid is, it has on board both a visible imager and a near-infrared spectrometer and photometer. So Euclid can do both photometry, imaging, and spectroscopy. And besides all the specification, okay, more than 1 billion images, more than 30 million spectra of galaxies, out to redshift 2. But besides all the specification, I want you to focus on this 1% accuracy that Euclid is expecting on the matter power spectrum for the measurements of the matter power spectrum. Why it's important is 1% accuracy? Because this is the figure that I showed you before. So in the worst case scenario, minimal neutrino mass, this effect is about 3%. So one might think, okay, it's a 3%, I have a 1% accuracy on my measurements of the matter power spectrum, it's done. I will be able to measure the neutrino mass. Unfortunately, this is not the case, because the impact of massive neutrinos is mainly located on scales that are very difficult to model. So we have a challenge. The challenge is to get a 1% accuracy also on the theoretical predictions. But this is difficult because we have several systematic effects and theoretical uncertainties. First of all, we have the galaxy bias. So what we measure with the survey, with the spectroscopic survey, are galaxies. But in order to extract the cosmological parameters, including the neutrino mass, we need to reconstruct the matter power spectrum. And the two quantities are related by this bias factor that is very difficult to model. In particular, in the case of neutrinos, the bias factor should be modeled with respect to the colder matter only power spectrum, so without taking into account the neutrino perturbations. Why? Well, because we have said before that neutrino free stream. And the typical scale of neutrino free streaming is about 1 gigaparsec. So neutrinos do not cluster on the scale of a galaxy. That's why we have to look for the suppression in the colder matter power spectrum only, rather than to the suppression in the total matter power spectrum. So remember, as I said before, this is about 80% of the total effect. If you don't do so if you model the bias with respect to the total matter power spectrum, you end up having a biased value of the sensitivity to the neutrino mass. Then, besides galaxy bias, we also have nonlinearities. So on small scales, the clustering becomes nonlinear. And nonlinearities are, once again, very difficult to model and to predict. We have to extract nonlinearities from n-body simulations. But n-body simulations are expensive, so we cannot run an infinite number of n-body simulations. So what we can do is to have a suite of few simulations and then use some emulators or some fitting formulas. But as you can see here, different fitting formulas and emulators do not agree among each other. And on top of that, we also have that different simulations do not agree among each other. So we still don't have this 1% accuracy on the theoretical modeling of nonlinearities. Then finally, on small scales, we have one more source of uncertainty, which is the baryonic feedback. So baryonic feedback accounts for all these processes like gas cooling, supernovae feedback, and the impact of AGNs. And as you can see, once again, different hydrodynamical simulations taking into account baryonic feedback do not agree among each other. So we have a theoretical error here. And I'm not sure if you can see here, but even if you have a conservative cut on your data, then you have a small impact due to the uncertainty on the modeling of baryonic feedback. So taking into account all these systematic effects and theoretical uncertainties, we worked on this forecast of the sensitivity of Euclid to the neutrino mass. So what we have here, this is a triangle plot with the cosmological parameters, including the sum of neutrino masses for the primary Euclid probes. So in gray, we have the spectroscopy. In red, we have the photometry. In blue is the combination of the two. So I'm not going through the details of these marginalized posteriors, but let me just say that there is a great complementarity between Euclid spectroscopy and photometry, and this complementarity is key to detect the neutrino mass. Then on the other side here, this is the same triangle plot, but here we have the combination of Euclid primary probes with CMB. So in orange, we have the combination with Planck, and in green, we have the combination with future CMB experiments, CMB stage 4 and Lightbird. So, okay, thanks. So let me jump to the results, to the constraint on the neutrino mass. So if we combine Euclid with Planck, so with current CMB, we have more than 2 sigma evidence for a non-zero neutrino mass sum. And if we combine Euclid with future CMB surveys, we can reach up to a 4 sigma detection of a non-zero neutrino mass. But of course, we have to remember that cosmological results are always model dependent. So these are the results that we obtain in the standard lambda Calder matter model. If we drop lambda, the cosmological constant, and we replace it with a more flexible phenomenological parameterization of dark energy, this W0 WA parameterization, then we lose about a factor 2 in sensitivity. Anyhow, we still have a detection of a non-zero neutrino mass. So given that we have this fantastic sensitivity to the neutrino mass sum, one might wonder whether Euclid will also be sensitive to the neutrino mass ordering. So what we have here is indeed the sum of neutrino masses in inverted ordering and normal ordering as a function of the lightest neutrino mass. So in green, we have, this is 1 sigma and 2 sigma from Euclid plus future CMB, stage 4 and Lightbird. And you see that this combination can rule out at about the 2 sigma level the inverted ordering. But we have to keep in mind that these are just forecasts. These are not real data, okay? So this forecast assume that the true neutrino mass is 60 milliV. Of course, if the true neutrino mass is not 60 milliV, so it's larger, 0.08 electron volt, then this gray and this orange bands will go up, will move up, and we will lose our sensitivity to the neutrino mass ordering. And on top of that, we have to keep in mind that these cosmological results are not sensitive, are not directly sensitive to the neutrino mass ordering, but they're only directly sensitive to the sum of neutrino masses. Indeed, this is the ratio of the matter power spectrum for the same sum of neutrino masses modeled according to one of the true hierarchies, so either inverted or normal, compared to the neutrino mass model according to the cosmological approximation, the so-called degenerate approximation, so M1 equal M2 equal M3. And you see that there is a small impact, but this impact is at the level of the few per mil. So it's nothing that we can really see in current or even future cosmological surveys. So with this, I will move to the conclusions. So Euclid has the potential to detect a non-zero neutrino mass. It also has the potential to put some pressure on the inverted ordering of neutrino masses. However, it is not directly sensitive to the neutrino mass ordering like other experiments, Juno or Dune. And on top of that, we have to keep in mind that all these cosmological results are model dependent and we have a lot of systematic effects and theoretical uncertainties that we have to keep under control. So the complementarity with ground-based experiments is key in order to obtain a robust detection of a non-zero neutrino mass. And then I will conclude with an open question. So what if we will have a tension between the cosmological bounds and the bounds from the lab, from ground-based experiments? So what if, for instance, scattering will detect a neutrino mass of 0.3 electron volt, and this is already in tension with the current cosmological bounds. So I will leave with this open question, and of course, stay tuned for the amazing Euclid results.
See, that's better.
Thank you. I have two questions. So the first one is related to this alternative to the lambda CDM model with time-dependent dark energy. Maybe you said it and I missed it, but can you remember me how W0 and WA are defined?
Yeah, sorry. W0 is the equation of state parameter of dark energy. WA is the redshift dependence. So it's not constant anymore, but it's A stands for the scale factor, so it's the redshift dependence.
And the second question is to try to clarify my confusion. So if I understand correctly, all forecasts are limits that are presented, like the one by Daisy, on the sum of neutrino masses, assume degenerate neutrino masses. That's correct. Now, did you say that if we take different masses for the neutrino, we get just 1 per mil difference? Okay, so in other words, even though, suppose I want to test or exclude the inverted mass hierarchy, I should scan over all possible masses for M3, the lightest neutrino mass, including 0. So naively, I would say that one should take, let's say, 2 degenerate neutrino masses and the other one 0. But do I understand correctly that if you do that, you will get the same result as if you assume that they are all degenerate?
Okay, yes. Let me clarify this. So if we approximate the two hierarchies with one massless and two massive, or with two massless and one massive, then the deviation is more than few per mil.
Okay.
But if we assume the degenerate hierarchy with respect to the true ones, so taking into account the delta m square, then this is few per mil.
Okay.
So, so basically, we can safely keep this approximation without biasing our results. The reason why in cosmology we use this approximation is that if you take your Boltzmann solver, whatever, CAM or class, basically 80% of the time is spent in solving the Boltzmann hierarchies for massive neutrinos. So if you assume that they have the same mass, then you reduce by almost a factor 3, your CPU time. So that's why, since we have to do something like 10 to the 5 realization, then it's a lot.
Yeah.
No, we don't.
Sorry.
Okay,
No, in the sense that, in principle, the suppression of the matter power spectrum could be sensitive to the different mass of each neutrinos. But I don't think that in the next experiment I have the sensibility to...
No, indeed. If you look at this plot, yes, you see that there is a small difference because basically the free streaming scale as well as the redshift of the non-relativistic transition depend on the on the individual mass. So this is why you have this small effect, but it's way too small to be detected. So this is few per mil, and we are hoping for a few %. to see a few percent. So it's one order of magnitude. In principle, there are some ideas of detecting the neutrino mass ordering with cosmological data from 21 centimeter line intensity mapping. Because basically with line intensity mapping, you can extend your redshift up to the point where you can see the non-relativistic transition of neutrinos. But this is, I mean, it's not going to happen with SKA or even PUMA experiments, surveys.
No, just a curiosity. Stefano is not here, so I cannot ask him. Ptolemy experiment, in principle, can also detect the mass in addition to the relic neutrino background. How competitive is, I mean with the Catherine, better than Catherine?
Okay, I'm not an expert. As you said, you should ask Stefano. But but the timeline of Ptolemy is not the timeline of Euclid or the Vera Rubin Observatory, I'm afraid.
It's really futuristic.
So yeah, probably it is competitive, but still
it is still at a prototype level. Huh?
Yeah, is it clear if Ptolemy will be able to detect CMB neutrinos? I don't think it's clear. As you said, Christina, it's at the prototype level.
So the timeline will be Euclid and even LSSD, I think, will be before we will have the results. The final survey, the full F-sky before Ptolemy. Yeah, being optimistic.
Thank you. Okay, in this, I think there is a sort of elephant in the room, in the sense that if one wants, there are a lot of, let's say, issues, anomalies, and tension in lambda CDM. If one uses all those tensions, first of all, the dark energy is much more complicated than with 0, 1. Second, the values of MAB or the neutrino mass goes okay, completely erratic. I'm working on this with, for instance, Cosmoverse, and they are planning to use all together. So maybe it's better to use also the expansion of the universe, Pantheon, the small scale, everything, and because maybe the anomalies in the things that we want to know in the expansion of the universe is not only the mass of the neutrino, but also other things that we don't know. And then using only this doesn't, so you have 64, no, for Hubble constant. Maybe it's not 64, just to give you one example. So one should consider all this tension, and the people they do, there are hundreds of papers, and if you look, the forecast for neutrino mass is much, much worse than the one you have given.
I agree, and indeed this is one of my backup slides with the constraints that you can have from current data on the neutrino mass. You say changing the lambda CDM model, but we have also other ingredients. First of all, we have GR. So basically, we can also change the GR. We can also change neutrino physics. So for instance, we can have neutrino interactions or decaying neutrinos. So as a disclaimer at the beginning, I say this is true in lambda CDM and with standard neutrino physics and in GR. Of course, if you change your model, this is Bayesian statistics, so you will change your constraint, but in my opinion, you also have to be careful about the model. So it has to be something that is physically motivated. We cannot just throw into the MCMC, into Bayesian statistics, 50 different parameters and so on and so forth, because otherwise you are losing the link with the cosmology, with the physics. So, for instance, there are the DESI collaborations also try to fit a negative neutrino mass, but it's a negative neutrino mass. So you can fit a different lensing, but then you are changing Einstein. So you have to be careful about it's Bayesian statistics. So whatever you throw in, it will give you some confidence intervals.
So the dark energy, for instance, you have fitted the dark energy with 0, with 1. This is one or the simplest, okay, that one say. And this does not solve, for instance, the tension that you have in agent 0, in sigma 0, and so on. They have. So usually they use more complex, sometimes even, and let's say, in unknown functions of the redshift of the lambda. So this is just one of the things. So I'm not saying that one has to give start with negative masses, with killing cosmology, everything like that. But I'm saying that the tension of the standard lambda CDM model that they are already, they make as a byproduct that neutrino masses enters with the values, for instance, of H naught now, or the expansion of the universe are redshift to 1. So they are all related. And at the end, it could be unhelpful, because sometimes the degeneracy breaks down because they are related in this way. Or can be worse, that the degeneracy increases. But what I'm thinking that Euclid will go in this way, to put together his result with Pantheon result, with the supernova result, with the Bow result, all together, because at the end, the universe is one. And so at the end, it is already related to the expansion of the universe.
Sure. And I will also add that about the Hubble constant tension, first of all, you have to understand if it's a tension, right? So first of all, you have to check, carefully check.
The origin is not known, but the tension it is. So it's absolutely sure that it is the tension.
Yeah,
the origin is unknown.
But how? I mean, are we sure that there is no systematics in that?
No one can be.
Okay.
No one
So
can
maybe.
be sure.
Yeah. No. There is not too much. We are here to discuss. I mean,
So,
that's the object of the.
I have two comments. One is following on this one. So I only attend neutrino conferences primarily, so maybe I'm biased in, maybe the talk is biased in the emphasis. What's more interesting, measuring the neutrino mass hierarchy or finding out that lambda CDM is like not the description of of cosmology? Right? Because we're focusing on the first thing, but to me, I'm a neutrino physicist, and I think the second thing is more interesting.
Indeed. Okay. And it's also the other way around, right?
Sure.
So if, for instance, take light sterile neutrinos, these are already excluded by Planck, okay? And it will be even more including CMB stage 4 and also Euclid and so on and so forth. But think about the possibility that the ground-based experiments that we just heard about will see a sterile EV sterile neutrinos. This will be, I mean, in my opinion, this will be great. It will be a great challenge because it means that one of these three ingredients that we are using is wrong. It has something, it has to be adjusted,
Yeah.
at least. So, so yes, one possibility is to include also the supernovae measurements, so to have some handle on the other on the other observables beyond CMB and large-scale structure. One possibility, in my opinion, I'm afraid that one possibility, especially with large-scale structures, we have to be very careful about systematic effects.
Yeah.
Because it's, I mean, I didn't go through the details, but it's a really tricky business. What I show you is only one bias, but in reality, with Euclid, we will have something like 50 nuisance parameters with linear bias, non-local bias, and so on and so forth.
Yeah.
So
it's more of like a messaging comment, I guess, than anything else. Like I was a part of like CMBS4, like of the collaboration or whatever, and when you hear the discussions of CMBS4, something they're really stepping forward with is we're going to get us closer to measuring the neutrino mass hierarchy. But like, you know, is that instead, let's say we're going to learn more about like the origin of the universe, right? Like that. It seems like there could be a better balance there, or like say we could look at it this way, or we could look at it this way. So that's just my outside perspective as a neutrino experiment.
Yeah, right. But one of the important points is indeed to do some neutrino physics with cosmology, so that we have a test bench.
Sure. Yep.
Because otherwise, if we only talk about dark energy and nothing that can be tested with ground-based experiments, then we cannot see the tension, and if we don't see the tension, that we do not learn anything about the model, the underlying model. So it's also the other way around.
Sure.
It's complementarity.
Yeah, and then the other question I had was more technical. Euclid, so it's taking data now, or it just got launched? Can you remind me of the timeline?
The launch was 1 year ago, exactly 1 year ago.
So it's taking data, and it'll take data for 6 years?
Yes, yes. And this one is one of the reconstruction of the images from Euclid.
Yeah, so basically, before 2030, there will be new results from Euclid. Like for neutrino physics, Dune starts up 2030-ish. And that's like, and Juno will start in 2025, so maybe by 2030, you'd be looking at 2-3 sigma from there as well. Who knows what's going on with CAM3net? We'll see how that progresses. But 2030, that's kind of, us neutrino physicists, that's an interesting day.
Yeah.
Okay. Are there further? See, Georgia. See.
Can I follow up on the previous point just a little bit? Because I also kind of share the same picture with Bryce here. So you gave the example of sterile neutrinos, but what if it's just 3 neutrinos and we know the mass hierarchy and we might maybe even know something from Catherine? To what level do you need to know these numbers in order to be able to say that you've confirmed lambda CDM is not right, or that you've been able to differentiate between some beyond lambda CDM model and another? Is there like a number? Is there a percentage, or no?
Well, if we have, well, first of all, we have the first problem is if the cosmological measurements will go below 60 millielectron volt. Then we already know that there is a problem, right? Then on top of that, whatever tension, I mean, if Catherine will find, I don't know, a 0.3 electron volt with a 90% confidence level, then we already know that the bounds 72 millielectron volt from DESI plus CMB, it's somehow, I mean, we know that there is something wrong. We still don't know what is wrong, of course, but in order to understand that, for instance, if you have so if you have a modification of general relativity, you can hide the effect of massive neutrinos on the matter power spectrum. So next thing you have to do is to test these kind of models, whatever if it's changing GR or if it's non-standard neutrino interactions in cosmology, and then also find some tests with ground-based experiments, for instance, with the neutrino experiments for non-standard interactions. If there are some light mediators, you can also look at the supernovae, so the energy spectrum from distortion in the energy spectrum from supernovae. So you have to add more ingredients, more observables to understand that.
Sorry, can I just get clarification? You kind of said that the DESI results are inconsistent with lambda CDM, and then just, kept talking. Can I just understand, just push, I'm not pushing back, I just want to just, I guess, understand that a little more. So my understanding is that the DESI results are consistent with lambda CDM, you get some set of parameters, but then when you compare the parameters that are measured by DESI to other experiments, then you get attention. But analyzed by itself, the DESI data is quote unquote consistent with lambda CDM. Is my interpretation true, or is that, can you expand on that?
Okay. So it's not DESI alone. It's a combination CMB. They have CMB, Planck, and ACT, and DESI. This combination is about 2.3, 2.5 sigma away from lambda CDM. If you take DESI only, then these will reduce to about 1.5 sigmas. So it's the combination CMB plus DESI. That is, okay, it's so not DESI really, DESI itself is 1.5 sigma away from lambda CDM. So from this point here.
So by away from lambda CDM, you mean when you compare to the alternative model, which is?
So the bias ratio.
Yeah.
Yeah,
I guess I'm just trying to understand it. Is let's say DESI is your only data set in the entire world, which is of course not true. Mm-hmm. And is that data, can you get a good fit to the DESI data with just lambda CDM? I was under the impression that was true, but unless I was mistaken.
The delta chi-square is worse. Now I don't remember exactly how much is the delta chi-square. I should look at the paper, but delta chi-square is worse.
Okay. Worse than the alternative, which is varying dark energy.
Exactly.
Okay.
Exactly. But I'm not part of the DESI collaboration, so I should really look up at the paper.
So just to follow up to Louis, and Planck is okay with lambda CDM, then Planck is not okay with lambda CDM. How does that happen?
Sorry, can you?
So following up on Louis' comment, DESI is okay with lambda CDM, Planck is okay with lambda CDM, Planck plus DESI is not okay with lambda CDM. Right. How does that happen?
Because, again, I'm not speaking. I'm not part of the Planck collaboration or the DESI collaboration either, so I'm speaking only for myself. But the point is that you are fitting some tensions. That's what you are doing. You are extending your parameter space. You have more freedom, so you can fit something fishy that is in the data.
Yes, I agree with you. It's very complicated because it's highly nonlinear. When I said before that if you just open a new parameter, you can know what's going on in the other parameters. And so it's perfectly, consistent. The fact that the two of them separately, they are, say, in agreement with V0, 1 and V1, 0, vice versa. And but when you put together, it's different. because it's very, very really complicated and non-linear, let's say, constraint.
If I can add, indeed, if they fit with a negative neutrino mass, they get a better kite. Of course, the neutrino mass is not negative, but what you are doing is that you are fitting something that it's in the data, but you are not properly modeling. So that's why you get a better fit with a negative neutrino mass.
Just a small comment. So I think, like, my understanding from the DESI fits is that it fits lambda CDM or WCDM, where you just have one equation of state parameter that's free, consistently with lambda CDM. When you add another parameter, W0, WA, so you have two equation of state parameters, there's a mild preference for that model for DESI on its own, like you said. But I think Planck doesn't, on its own, prefer W0, WA, CDM, because I don't think it can constrain W0, WA, because you only have like one redshift. I think you need a redshift evolution, right? So it can't really fit that model anyway, which is why when you combine them, you see a different constraint for the W0, WA model, or a preference for it. I can't remember off the top of my head, but it's a mild preference, I think, for Planck and just DESI, but obviously it gets stronger when you add the supernova.
Yeah, DESI alone is 1.5, and the combination of the two is 2.
Yes, I had a comment about this problem. The inconsistency is more between DESI and CMB and the supernovae pantheon and union, because if you consider only DESI and CMB, they are roughly in agreement, while if I add supernovae data, this is the main problem.
But this is also DES year 5.
Yes, Pantheon Plus or Union 3, or yes.
Okay, but to the supernovae.
Since you are including the H0 measurements in this, of course.
Yeah,
I mean, the problem is that if you put some data concerning H0 that are not from Planck or CMB, you are putting aside some material, of course, drives everything towards...
Exactly. One has to be careful in fitting data that are, taken separately, they are inconsistent.
I agree that, of course, putting more information can be useful, but when you put a lot of information inside, a study, you can encounter problems due to the fact that are different experiments, each of them with the systematics and so on. The situation, in my opinion, is very similar to the one that is a lab experiment. For example, when the people try to do the global fit for stellar neutrinos, also there is a mess, appearance, disappearance, and different experiments, each of them with all systematic and so on. So I agree that in principle, to consider all the data available can be useful, but pay attention that when you do this, you are considering everything that sometimes is not the best.
The point is that when one want to fit to, let's say, see the expansion of the universe, one has to put neutrino masses because enters also this neutrino mass. Okay, so then and when BAO are measurement of H0. By the way, the BAO is another way to measure H0. So there's not much difference between the expansion of the universe of a supernova or the values of BAO. So what comes that one wants to put together all the expansion of the universe from zero out to the at the beginning of the universe, and one finds a lot of tensions. And between these tensions on the standard model, if one wants to solve the tension, okay, then in some cases the neutrino masses pay a price. So you have the neutrino mass much higher, or zero in some cases, but just to say that the situation is complex. If you do only by let's say the CMB, I agree that you can find one solution. But the point is that you cannot neglect the other people, and there are a lot of effort over the world to understand the lambda CDM as the evolution and so, finds that this evolution is complex, is more complex than before, and as byproduct, that I agree perfectly on what say before, what product that for us is not so important, but one of the byproduct is that the neutrino masses, or the sum neutrino masses, is not so certain, because it's much more dependent on the water we put. But we have to put this, because these tensions are very, very big. Okay, so just to give an example, if you measure a G naught from, in a way you obtain something like 70, more than 75, even more. If you get in the other, you get at the level of 80 sigma less. This is just one of the many.
I think. Okay, last comment. I think that this is really one of the things that it will be discussed a lot these days. So we will have the lunchtime and coffee breaks and many other sessions. So
last comment. I agree that there is a serious problem with H0, but I remember, and Maria for sure can say better than me, then, for example, 3-4 years ago, where we tried to solve the H0 tension increasing and effective. But then there was an according with H0, and there was a problem with the sigma 8. So, I agree, but the problem, as you say in Italian, esce dalla porta, entra.
Can I just say, just just a disclaimer. Of course,
being the speaker, you have the right one.
What I presented is a forecast for the Euclid corroboration. So it does not reflect all the possibilities that are interesting for neutrinos in cosmology. But you need an estimate of what your satellite can do. So you get this estimate in your lambda CDM model, which right now, currently, is the only one that you can know. It goes through all the different observables.
Okay, thank you very much.